Hello and welcome to this lecture on error control coding. My name is Sumit Kumar Chobe and today I am going to discuss BCH code, actually part 1 of the BCH code, that is encoding. So BCH code forms a class of cyclic code that are constructed using polynomials over finite field. BCH codes were invented by Alexis Hockenheim and independently in 1960 by Raj Bose and D.K. Roy Chaudhary. The acronym BCH comes from the surname of their inventor, mistakenly in case of D.K. Roy Chaudhary. The BCH code are very powerful code in the sense that you can actually control the number of error correcting capability you want in these codes. Okay, they are basically cyclic codes. These codes are you can say that remarkable generalization of Hamming code for multiple error correction. We are in this lecture going to consider only binary BCH code, that is also called primitive codes. Okay, and non-binary codes like Reed-Solomon codes will be discussed in the next lecture. Now the description of the BCH code. For any positive integer m greater than equal to 3 and t less than equal to 2 to the power m minus 1, there exists a binary BCH code with the following parameter. The very first parameter is block length n equal to 2 to the power m minus 1. So block length is actually equal to 2 to the power m minus 1. Number of parity check digits n minus k is less than equal to m times t, where t is basically the error correcting capability of BCH code. Minimum distance d minimum is greater than equal to 2t plus 1. So that's why t is your error correcting capability. Okay. So as you can see that in this code, even in the description of these code, we have the error correcting capability directly built in. So one can actually control how much error correcting capability he wants in his code. Okay, so this is the reason why BCH codes are also called T error correcting BCH code. Now let's consider alpha to be a primitive element in GF2 to the power m. The generator polynomial gx of T error correcting BCH code of length 2 to the power m minus 1 is the lowest degree polynomial over GF2, which has alpha, alpha square, alpha cube all the way up to alpha 2 to the power t as its root. Okay, so you can say that g alpha to the power I is actually equal to 0 for I between 1 to 2t. So gx has alpha, alpha square, alpha cube all the way alpha 2t and their conjugates as its roots. Okay, so let phi ix be the minimal polynomial of alpha I, then gx must be the least common multiple of phi 1, phi 2, phi 2t x, right? So gx is simply LCM of phi 1x, phi 2x and all the way up to phi 2tx, where phi x is basically minimal polynomial. Okay, now let's consider that I is an even integer. In that case, I can always be represented as I is equal to I dash into 2 to the power L. For example, 6 can be written as 3 times 2 to the power 1, isn't it? In the similar manner, if you have some positive integer 8 can be written as 1 times 2 to the power 3. So you can see that if you have I as even integer, then it can always be represented in this form. Okay, then alpha to the power I will be equal to alpha I dash 2 to the power 2l. What that means, that alpha I is actually equal to alpha I dash to the power 2 to the power l, and we know that beta and beta 2 to the power 2l is actually going to be conjugate of that, right? They are going to be conjugate. So in this case, alpha I and alpha I dash is going to be conjugate of each other. In that sense, the primitive polynomial with respect to alpha I and alpha I dash is going to be the same, right? Okay, so so we can say from therefore that phi of 2t will be equal to, since 2t is always going to be a even integer, right? So its polynomial is already going to be, you know, phi of t. So phi of t and phi of 2t is going to be similarly going to be the same thing. So using this property in mind, we can say that generator polynomial is basically LCM from phi 1 to phi of 2t minus 1. We don't have to consider 2t, phi of 2t, as phi of 2t will be the same as phi of t. Okay, so the degree of gx at most is equal to m times t. That is the number of parity check digits n minus k of the code is at most equal to m of t. Otherwise it's generally less than equal to this value. If t is small, if the error correcting capability of the code is small, then n minus k is exactly equal to mt. Okay, if t is very small. Since alpha is a primitive element, the BCH code defined are usually called primitive or narrow sense BCH codes. Okay, so now we are going to see one of the encoding example for this BCH code, and it's actually a very simple problem, but this problem happens to be asked in the university examination in 2018, May 2018. So we have to find out the generator polynomial for a BCH code with block length n equal to 15. So the first thing that is given is n is 15, right? And the error correcting capability TC is equal to 2, right? Now use primitive polynomial x for x plus 1 over gf2 to the power 4. So we have to find out generator polynomial, and the Galois field that we have to consider, finite field gf2 to the power 4 that we have to consider, has to be generated using x to the power x to the power 4 plus x plus 1. Okay, so using this in mind, you can already say that alpha to the power 4 plus alpha plus 1 is going to be 0, as alpha is going to be alpha is going to be the root of primitive polynomial, right? So this must be accurate. So we can say that alpha 4 will be equal to alpha plus 1. Another thing is that alpha to the power 15 is going to be equal to 1. So using these two these two relation, we have to first find out what you can say primitive polynomial. We have to find out minimal polynomial. Okay, but we will consider that later. Now let's just think about BCH code for a minute. Say if we have gx as the generator polynomial of BCH code, then it will be equal to LCM, since t is equal to tc is equal to 2, right? So this will be equal to phi 1 of x comma phi of 2 of x all the way up to phi of 2t minus 1, means phi of 3 of x. So you see that gx will be LCM of phi 1, phi 2 and phi 3. Phi 4 we have already seen that we consider only all the way up to 2t minus 1, right? So you can see that phi 1x and phi 2 of x, these are going to be equal. Why? Because alpha and alpha square both are conjugate. So you can say that primitive polynomial with respect to each other with phi 1 with alpha and alpha square is going to be the same. Okay, right? In the similar manner, we can say that gx will be actually LCM of phi 1x and phi 3 of x, because phi 1 and phi 2 is basically same. So you can say this is actually phi 1 of x times phi of 3 of x. Okay. Now to calculate what you can say to calculate minimal polynomial, we have to actually consider the Galois field that is generated using x to the power 4 plus x plus 1, right? So this is the Galois field that is generated using that, and we have to consider this to actually find out what is our phi 1 of x and phi 2 of x. Okay, so phi 1 of x here in this case will be actually equal to phi 1 of x will be actually equal to x plus alpha into x plus alpha square into x plus alpha cube into x plus alpha to the power, not cube, alpha to the power 4 and x into alpha to the power 8, as these are going to be your what you can say, this is going to be, these are going to be conjugate. Alpha has conjugate as equal to alpha square, alpha 4 and alpha 8. These four are actually conjugate of each other. So using this we can actually calculate this. Now if you consider this, then if you multiply this, you will be having x square plus alpha square times x plus alpha cube. This is one of the factor. Second factor will be going to be x square plus alpha 4 plus alpha 8, right, times x plus alpha to the power 12. Okay, so alpha plus alpha square, you see alpha plus alpha square is actually equal to alpha to the power 5. Now alpha to the power 4 plus alpha to the power 8. So alpha to the power 4 is alpha plus 1, alpha to the power 8 is alpha square plus 1. So this is again going to be equal to alpha square plus alpha, and that is also going to be equal to alpha to the power 5. So we have now, this phi of x as phi of x as, it is phi 1 of x as x square plus alpha to the power 5 x plus alpha cube times x square plus alpha to the power this is again 5 of x plus, and then you have alpha to the power 12, right? So if we multiply these two together now, what is the result? What's going to be our result? This is something that we have to consider, right? So this is going to be x to the power 4, right, plus alpha to the power 5 x cube plus x square alpha to the power 12, and then we will have here, we are going to multiply with alpha to the power 5x in the second polynomial, and you will be getting alpha to the power 5 x cube plus alpha to the power 10 x square plus, here again I am going to get alpha to the power 17, but alpha to the power 15 is actually equal to 1. So this is again, you are going to have alpha square and x, right? In the third scenario, what I'm going to get is, here if I will multiply this, I will be getting alpha cube x square alpha 8 of x plus, this is alpha to the power 15, which is equal to 1. So if I will add if I will add all of them together, the result is going to be equal to, so the result is going to be equal to x to the power 4. If you add this and this together, since this is basically XOR, right? So these are going to be the similar, so they are going to cancel out each other. So with respect to x cube, you have only 0. Now with respect to this, if you add x square here, so for that you have to actually see, we are actually adding alpha to the power 12, alpha to the power 10 and alpha cube, right? So what is this actually equal to? So we have to see the Galois fill, and you see that alpha to the power 10 is actually equal to alpha square plus alpha plus 1, right? Alpha to the power 12 is equal to alpha cube plus alpha square plus alpha plus 1. So if I add alpha to the power 10 and alpha to the power 12 here, if I add these two together, then I will end up with alpha cube, and then I am going to add alpha cube here, right? So this is also going to cancel each other, isn't it? So this is also going to cancel each other, and this will result in 0. And here in this case, you will be having alpha square and alpha to the power 8, and alpha to the power 8 is actually equal to alpha square plus 1. So this is alpha square plus alpha square plus 1. So we will have 1 times x. So this will result in x, and then 1 is going to be there. So the minimal polynomial phi 1x with respect to this is actually equal to x to the power 4 plus x plus 1. Okay. In the similar manner, we can also calculate what is going to be our phi of 3 of x, because these are the two things that we have to actually consider, isn't it? So let me do that. So now I am going to consider phi of 3 of x, and phi of 3 of x, to do that I am actually have to calculate all of the all the conjugate of alpha cube, right? So alpha cube conjugate is alpha cube, alpha to the power 6, alpha to the power 12 and alpha to the power 24, which is equal to alpha to the power 9. So alpha cube, alpha 6, alpha 12 and alpha 9, these are going to be the conjugates, right? So now our polynomial, primitive polynomial phi of 3 of x is going to be x plus alpha cube into x plus alpha to the power 6, x plus alpha to the power 9 and x plus alpha to the power 12. So let me multiply alpha cube and alpha 12, that will be much easier, and let me multiply these two together. So here I will be having x square plus alpha cube plus alpha 12 whole time x plus, then we will have alpha to the power 15, which is equal to 1, and here in this case actually we are going to get x square plus alpha to the power 6 plus alpha to the power 9 time x plus 1, which is we are also going to get alpha to the power 15 there, right? So these are the two things that we got. Now I have to actually find out what is alpha cube plus alpha 12 is. So alpha 12 is actually equal to alpha cube plus alpha square plus alpha plus 1, and if I will add alpha cube here, right, so I will end up with alpha square plus alpha plus 1, and alpha square plus alpha plus 1 is actually equal to alpha to the power 10, right? So we will get alpha to the power 10 here. Let me consider now alpha 6 and alpha 9. So alpha 6 is alpha cube plus alpha square, alpha 9 is alpha cube plus alpha. So alpha cube is going to get cancelled, and I will end up with alpha square plus alpha and alpha square plus alpha is actually equal to alpha to the power 5. So here I got alpha to the power 10, here I got alpha to the power 5. Okay, so this is alpha to the power 10 and this is alpha to the power 5. So our next step will be to reduce, to simplify this polynomial. So let me just consider this only, and so phi of 3 of x will be equal to x square plus alpha 10x plus 1 time x square plus alpha 5 of x plus 1, and if I will multiply these two together, I will end up with x to the power 4 plus alpha to the power 5 x cube plus x of square, and here again if I will multiply with alpha 10, I will get alpha to the power 10 x cube and then alpha to the power 15, which is again going to give me 1 only, right? So I will get only x square here, and then if I will multiply alpha 10x into 1, I will get alpha 10x. In the third case, I will be getting x square here, right here, and then I will get alpha to the power 5 of x and then 1, right? So if I will add them together, the result is going to be fairly simple, right? It's simply going to be, you see, x to the power 4 here, and then I am adding alpha to the power 5 and alpha to the power 10, and you can see that from here only that alpha to the power 5 and alpha to the power 10, alpha to the power 5 is alpha square plus alpha to the power 10 is alpha square plus alpha plus 1. So alpha square plus alpha will get cancelled and I will have only 1 only, right? So I got x cube. The second answer is going to be x cube. Here again 1 plus 1 plus 1, it is XOR, so odd times is going to be 1, right? So we will be getting x square, and alpha 5 to the power alpha 10 we have already considered, it was 1, so we will x plus 1 finally. Okay, so this is the result for phi of 3 of x, right? So now we have calculated both phi 1 and phi 2 of x, and we have to calculate g of x, which is basically the multiplication of it, right? So let's consider that and let's calculate that. So you can see here that phi 1 of x is calculated to be x to the power 4 plus x plus 1. Phi 2 of x is x to the power 4 plus x cube plus x square plus x plus 1, and we have to multiply these two together. When we multiply these two together, our result is going to be g of x, x to the power 8 plus x to the power 7 plus x to the power 6 plus x to the power 4 plus 1. Okay, so this is how we can calculate generator polynomial of a BCH code. So you see what are the steps involved here. The very first thing is that the formula of generator polynomial, which is equal to basically LCM of phi 1x, phi 2x and all the way up to phi of 2 TC minus 1. TC is basically error correcting capability, which is equal to 2 here. So 2 times 2 minus 1, phi of 3 of x, right? So we have phi 1 of x, phi 2 of x, phi of 3 of x, right? After that, we have to actually calculate phi 1 of x, phi 2 of x and phi 3 of x. We will see that we have already seen that phi 1 of x and phi 2 of x is basically going to be conjugate of each other, right? And so does the phi of 4 of x. If it was there, then you have to just multiply phi 1 of x and phi 3 of x in order to get your generator polynomial, right? So this is going to be phi 1, then you have to calculate phi 1 of x, and now to calculate phi 1 of x, you have to know the GF2 to the power 4, right, which is generated using x to the power 4 plus x plus 1. So this is the primitive polynomial which you have to consider now to generate GF2 to the power 4, and using the algebra of that, you have to actually calculate g of phi1 of x and phi2 of x, and then you have to multiply them together. Okay, so thank you for tuning in. You can find my if you have problem in calculating this minimal polynomial phi1 of x and phi2 of x or phi of 3 of x, then you can consider one of my lecture on primitive polynomial on minimal polynomial, that will be up there. Thank you.